In this question, we're going to be looking at section 7 from the December 2017 exam for Math 121. We're given that some positive constant K helps to define a patient's temperature change in degrees Celsius due to a dose of a medication. So if someone tells us how much dose we get, we're going to get a certain temperature change as a result, and there's that K value, that's some constant we don't know. The first question is what dosage, so here we're looking for a D value, maximizes the temperature change. So we already know the relationship, and we're trying to find out what value of D makes that a maximum. So if we think of the relationship, there's going to be some function, and we're looking for the peak, and of course, that's going to be a critical point. So one of the properties of that point is that the derivative of this function here is going to be 0, and the derivative we have to take is with respect to this capital D value. We're also told that we need to show that our answer is a local maximum, and of course that's a indicator that we need to use either the first or second derivative test. Because of course, derivative equals 0 is not only a property of maximas, it's also a property of local minima as well. So let's give that a shot. We're going to find our derivative first, and you can do this straight up if you like. I'm tempted to expand this though before taking the derivative. We have k over 3d squared minus d cubed over 4, pardon me. And with that, it becomes easier to take the derivative with respect to d, because then we're going to get k over 3 times 2d's minus 1 over 4 times 3d squared. And we're going to set that equal to 0 so that we can identify critical points. Now, what are we solving for? Again, without x's and y's, sometimes that can be a bit distracting, but we're solving for dosage. What dosage maximizes the temperature change? K will be along for the ride, but we want to solve for D. Well, if that's the case, what we can do is factor out a D out of both of those terms, and then we get a K over 3 with a 2 minus 3/4 D, and from that we're going to get D equals 0 as one possibility, or the more interesting one and the more likely maximum point is going to be this internal factor here. That can equal 0 as well. And if we set those equal to each other, or equal to 0, then we can solve for D. We'll bring that over. 2k over 3 is equal to positive 3/4 D, or D is equal to 4/3, 2/3 K. And that's 8/9 K. So we actually have two D values that do the job. I think for us at this point, it's kind of 6 in 1. First derivative test, second derivative test. Let's do the second derivative test here. The solutions show the first test. Second derivative test, we need to know the second derivative of our temperature change with respect to D, and we can differentiate this form here. That's probably easiest. That'll give us 2k over 3 minus 3/4, and then we differentiate the 2d, we're going to get another, we differentiate the d squared, we're going to get 2d's. And let's just tidy that up a little bit. 2k over 3 minus 3/2 d. And so at the critical point d equals 0, we're going to have this second derivative is equal to 2k over 3, and we were told that k is a positive constant, so that's positive. And so our graph is, I don't know where it is, but we have a flat slope. This is t against d, and we know it's concave up, and so it's going to be a local min. That's interesting, but it's not what we're looking for. Whereas at our other point, at d equals 8 over 9 k's, our second derivative is equal to 2k over 3 minus 3/2, 8/9 of k. There's a k in both of those, and the key thing is what else comes out of this. That'll be 2/3 minus the 8 and that comes as a 4. You can use your calculator if you like. 4 over 3. There we go. Which is minus 2/3 k. And so that's concave down. So on our graph, we know we have a critical point at 8/9 of k. Put this up here a little bit higher. So wherever that point is, we know it had slope 0. That's what this calculation told us. And now we have a negative second derivative. So we have concave down. And so this is going to be a local max for the temperature change. So our short answer is D equals 8 over 9k is a local max for the temperature change. There we go. All right. So that's a straightforward optimization problem in the sense that we already had a function, we had to differentiate it, set it equal to 0. There was the wrinkle that we had this unusual letter D and a K running around, so you had to be clear about what variables were doing what. But otherwise, the process was straightforward. Now this is an interesting variation. The sensitivity is defined as the derivative, dt dd. What dosage level is associated with the maximum sensitivity? All right. The key thing here is to recognize that we actually have a function already. From the first part, scrolling up here, we have the derivative is 2/3 k. I'm just going to paraphrase here, tidy up. 2/3 k times d minus 3/4 d squared. So whatever this function is, this function s against d, I don't know what it looks like, but it too may have a maximum. Well, where's that maximum going to occur? It's going to occur when the derivative ds dd is equal to 0. It doesn't matter that we took a derivative already. I don't care. Don't care at all. This is a function that I'm now interested in, ignoring the answer from part A. Sensitivity is this. Where does the maximum for sensitivity happen? It occurs when the derivative of sensitivity is equal to 0. So don't overthink it, is the key thing here. Sensitivity is this. It's going to have a critical point when the derivative is 0. So we just set the 0 value and take the derivative. We've actually already done this, but we'll do it here again. Minus 3/4 times 2d. And that's the same as 0 equals 2/3 k minus 3/2 d. Now I need to solve for d. What dosage produces this level? And so if we solve for d, bring that over, 3/2 d is equal to 2/3 k. And whoops, cross multiply a little bit here. We're going to get d equals 4/9. Not 8/9, but 4/9 here. And we're told in the question here, we do not need to show that it's a local maximum. So we're going to get an answer that the sensitivity, this separate function related to earlier ones, but separate fundamentally, is going to have a maximum at 4/9 of k.